So next up is Hans Christian Luedemann. He's the founder of Meniscense. His work is focused on solving the problems of rapidly and precisely measuring small amounts in a microplate format, a real challenge for many medical research and clinical labs. His presentation is titled Non-Contact Volume Measurement in Microplates for Process Quality Control, and I'm looking forward to this. Hans?
Thank you, Sam. Let me figure out if I can share my screen. Can you see my screen?
I do.
Awesome. Well, thanks everybody, and thank you in particular to the folks at LRIC for making this happen and for giving us an opportunity to present this work here. So, volume measurement in microplates for process QC. Why would you want to do that? Here's just a few examples of why people are interested. I'm just using this as an opportunity to set the stage for what we're trying to do. So one is inventory management. You want to know how much compound is left in a certain tube or a certain plate, so you can replenish your inventory in time and don't run out. Another big block, and that kind of encompasses most of these tasks, is process verification, and that starts with inputs. Is there, for example, just as an example here, is there enough of this patient sample to even begin this process? Is there enough that came off of this DNA extraction to begin our process? Those kinds of things. Then a big part is liquid handler quality control. Does the liquid handler do what we think it does or what we're telling it to do? And then the last part is monitoring process outputs. Are we delivering what we say we are? And that could be either in a commercial setting. Let's say you're making reagent kits, you're delivering plates that have certain contents per well, or you're in a compound management group and you're delivering assay-ready plates to your internal customers, and you just want to convince yourself and them that what you're giving them is what you're actually telling them. Now, what if you could have a technology that allows you to verify liquid volumes in line, in near real time, with really high resolution, in a non-contact way? What that would allow you to do is you could basically generate an audit trail for every sample as it moves through your process. Now, the Meniscense technology is a technology that allows you to do volume measurements in line. It works on any liquid. It is completely non-contact and non-destructive, and by extension then also sterile. It is very high resolution. The resolutions we've demonstrated range from about a nanoliter fill height resolution in a 1536 well plate to 10 to 20 nanoliter resolution in a 96 well plate. It works in all plate densities, and it works in plates and tube racks that are in SBS format. This is just a teaser of what a result looks like. So what you see here is a meniscus of an aliquot of DMSO in a 384 well plate, and then we're just adding a very well defined small aliquot to it. The way we make very well defined small aliquots is we use precision bearing balls and just drop them into the well. So in this case, these are 33 nanoliter volume. So that corresponds to just adding a very small volume to an assay ready plate, for example, as part of the dilution, and then convincing yourself that you've actually done that. And if you look at this, you can see that these 33 nanoliter additions are very, very well resolved. Now, how does it work? The technology works by measuring the distance to the liquid surface. And we're doing that by comparing optical path lengths. There's two optical paths. One path is the path from our sensor to the liquid surface and back. And the other path is a reference path, the length of which we can measure very, very accurately. From that, we get the distance to the liquid surface. From that, we get the fill height, and from the fill height and the plate geometry, we get the volume of liquid in the container. In a little bit more detail, on the left-hand side here is sort of a schematic diagram of the type of interferometer we use. So you have light from a light source hitting a beam splitter, where the wavefront is split, and part of the beam goes down onto the sample, and the other part of the beam is transmitted through the beam splitter and travels towards a reference mirror where it is reflected. The sample also reflects light back to the beam splitter, and then the beam splitter combines the reference path and the sample path, and the combined beam now hits the detector. We can vary the difference, the path length difference between the reference path and the sample path very accurately and keep track of that. If we do that, the signal we see on the detector looks like that signal that's schematically shown on the right-hand side here. So what you see in that signal is two features. One is just a very high frequency sinusoidal oscillation, and the other one is a much slower amplitude modulation of that signal, so a much more slowly varying envelope of that signal. The high frequency signal, that is due to interference between the two beams. And you can think about that as two wave trains, one moving down the sample path and one moving down the reference path. And as they get recombined, if the paths are equal to within an integer multiple of a wavelength of light, what happens is you have the peaks on one wave train and the peaks on the other wave train superimposed, so they constructively interfere, they magnify each other. So in the output signal, you have a relative maximum. If they're off by half a wavelength, what happens now is that you have the peaks on one wave train and the troughs on another wave train superimpose, and they cancel each other out. So you have relative darkness on the detector and the relative minimum in this high frequency signal. That's interferometry, and that's how the high frequency component works here. What's special about the type of interferometry that we use for this particular application is that we use a light source where you only observe this type of interference for a very narrow range of path length differences. That's called low coherence in interferometry. And we do that by using a light source, standard light sources, such as, for example, light emitting diodes or superluminescent diodes. And now in that case, so we monitor the amplitude of that high frequency signal, and when the sample path and the reference path are exactly equal, that's when this envelope reaches its maximum. And when we reach that maximum, we can measure the length of the reference path. From that, we get the distance to the liquid surface, and from that, we ultimately get the liquid volume. So that's a little bit more of an in-depth explanation of how this technology works. And anybody who's talked to me about this before will know that I can talk about this ad nauseum. I will not do that now. So just talking about what types of resolutions can we achieve. Shown here is two examples in 384 and 1536 well plates. What we've done is we've just repeatedly measured fill height profiles in these plates of the same aliquot, and then what's shown here is the solid black line is the mean of these 10 fill height profiles, and the gray lines are ±1 standard deviation. If we crunch all this data and look at it, we find that our fill height resolution is on the order of hundreds of nanometers, and that is, in this case, is basically limited by the encoder we use to measure the reference path length. In a 384 well plate, that corresponds to about 2 nanoliters of fill height resolution, and in the 1536 well plate, where the cross section of the well is smaller, it corresponds to about a nanoliter of fill height resolution. So very high resolution. We can also obtain very good accuracy, and we've done this by comparing gravimetric testing of distilled water aliquots with volume measurement using our technology. And you can see here that this graph is very linear, and there's two different ways you can look at the accuracy of your measurement. You can go aliquot by aliquot and compare your the measured volume using our technology with the mass that was obtained. And if we do that, we get inaccuracies that are around 1%. You can also just use all aliquots at the same time, and the slope of that curve should give you the inverse of the density. If we do that, we end up with inaccuracies a little bit better than 2%. So all in all, we achieve inaccuracies of better than 2%, which is very competitive with other technologies available to do fill height measurement that are not non-destructive and non-contact. And another practical example, these are racked tubes. So these are 96 well tubes for acoustic dispensing that are in a 96 tube rack. And what we've done here is we've taken a sample of 6 tubes, and we filled each tube with several aliquots of DMSO. This is typically used in compound management, so DMSO is the applicable solvent. And then for each of these aliquots, we've determined the mass of the aliquot using gravimetric testing, and we've measured the fill height, and that's all shown in this plot here on the left. Now, what's shown in this table on the right is the results of a thought experiment. So we're holding the data for one tube back from the whole data set and use the data for all other tubes to generate a calibration curve to calibrate fill height against fill volume. And then we use the data from the tube that we held back from the calibration curve and plug the fill height numbers that we've obtained for these tubes into that calibration curve and obtain volumes. And those volumes we compare to the measured masses for these aliquots, and that's how we get accuracy and precision numbers for each of these scenarios here. The reason I'm showing all this is that this is a true practical illustration of the performance that's possible with this, including both the very, very high resolution of our fill height measurement and the manufacturing tolerances of this particular type of tube, which of course are much the manufacturing tolerances are much larger than what we can achieve in terms of fill height measurement. So in a 96 well tube, low microliter accuracy and precision, and we've actually found with several other tube systems that seems to be pretty representative for what is possible with this technology, without previously calibrating specific labware. This is the slide I used as a teaser early on. So incremental additions to small incremental additions to plates in a 384 well plate, very high resolution. And if you plot the fill height linearly, it's a very nice linear regression. So it all makes sense and checks out. One thing we've been working on more recently, and it's a little bit of an earlier application for us, is to, in a non-contact way, measure the volume of droplets as they are dispensed, for example, by acoustic liquid handlers or other type of droplet dispensers. So the way we do that is we use our interferometer to measure the apex height of the droplet. So basically measure the height of the droplet at its center. You see here across the top of this slide, you actually see the raw data of what that type of interferogram that I showed earlier as a nice schematic looks like. And then you can see how we're extracting the envelope from it. And from that, we get the apex elevation of the droplet. We then also take an image of the droplet looking down onto the droplet and use image processing to determine the contact diameter or contact radius of the droplet on the surface. And those two quantities are actually enough to determine, given that we know the equation that governs the shape of liquid droplets on a surface, those two quantities are enough to determine the droplet volume. And we've shown this here for a number of droplets of different sizes. The droplet cross sections shown here are actually to scale. The images are not, but there are 100 micrometer scale bars in each of these images, and it's shown on both microscope slides, but also, for example, the middle droplet here is shown in a 1536 well plate. So very typical applications of what would come off an acoustic liquid handler, for example. So this is an example of one of our early stage instruments. So it's a self-contained plate reader type instrument that has a built-in PC. A single board computer controls the whole thing. You can also talk to it externally from a scheduling software. There's a REST API where you can send commands to basically perform the various reads, set plate types, and so on. So just to summarize, we offer volume measurement that is inline, works on pretty much any liquid, is completely non-contact, non-destructive, and sterile, is very high resolution, and works in plates and tube racks in SBS format in the sort of common densities. Thank you for listening, and that's the end of my slides.
And thank you very much, Hans.
It's an optical sensor, so we need to have our sample surface be pretty much perpendicular to the optical axis. So we need to hit the droplet in the center, if that makes sense. And we can find the center because we can take an image and from that find the center. If the droplet is really oddly shaped and doesn't really have a center, that's much tougher.
Excellent. And what about dispensed droplets?
Dispensed as in dispensed into another piece of liquid, or dispensed onto a surface?
The question isn't specific about that. I'm going to Yeah.
We've basically shown both. I mean, the droplets I showed on a surface. Those came out of a liquid handler, out of a nano dispenser type liquid handler, and I didn't show that, but we have just like we use precision bearing balls to have like a defined droplet, we've done this with droplets added incrementally to an aliquot already in the well. So we can do either.
Excellent. And how fast can it do a plate?
So that depends a little bit on how deep the plate is. It depends on the density of the plate. Currently, we think that 96 well plates we can do certainly faster than a minute. In many cases, faster than 45 seconds. And then, of course, the time goes up as you go to higher density plates, and you gain a little bit because you have to scan less depth. But that's sort of a guide.
And I think I have some clarification on the droplet question, which is, you speaking of dispersed, is in multiple droplets.
No, I meant dispensed, not dispersed.
Excuse me. Yeah.
Yeah. So if you had the droplet volume measurement that's shown on a flat surface, we would rely on we can only measure one droplet at a time. So
Got it.
So, I mean, we could conceivably, you could go find several droplets and measure those, but that would blow up the time.